I'm lucky to introduce 3 incredible judges who will be helping us out today. And they will be deciding our eventual winner, who will be announced at the Alpha Awards this evening. Please join me in welcoming Kirk Goldsberry of the San Antonio Spurs and Research Paper Competition alum, Will Edmondson of Major League Baseball, and Nate Silver. Each finalist presentation is going to last 12 minutes, followed by a session of Q&A from the judges. Please stay seated in between the different presentations, since we'll be moving through them pretty quickly. And finally, with all that out of the way, I'm thrilled to introduce our first presenter, Philip Myman, who will be talking about an open-sourced optical tracking and advanced esports analytics platform for League of Legends.
Thanks. Thank you. League of Legends is an excellent, wonderful, brilliant game. It makes $2 billion a year. There's 100 million people who play it, but it has a flaw. The data and the analytics that result from that data are very rudimentary. That ends today. We're going to have better stats. You can look at, here's what the game looks like. At the top is basically the stats that are provided by Riot. You have the kills, the deaths, the towers, stuff like that. For each champion, you can see things like the items that they bought, their kills, deaths, and assists, maybe some gold that they earned, stuff like that. Very, very basic. But when you're playing the game, there's so much more information. It's such a shame not to have it available. Riot does a good job of making this basic stats available, but it's just like having 60s and 70s style box scores for NBA games. There's so much more information. Look at this information. We have for all 10 champions, we have their summoner spell cooldowns, we have their health, their mana. Specifically, we can see all of their attack stats, their attack damage, ability, power, magic, resist, armor, movement speed, attack speed, anything you want for all of 10. That's Lux. She does pretty well. All of their cooldowns for all of their spells. Every champion has 4 spells, Q, W, E, and R. If you start playing League of Legends, if you get a coach, the number one tip that every coach will tell you is look at the minimap, look at the minimap, look at the minimap. So let's look at the minimap. The minimap is over there in the bottom right. That's a source of incredible amount of information. Look at all the XY location data there. None of it is available typically from Riot API. But we can get at it, and we're going to extract it. We've tried 4 different ways. 1 didn't work. The 3 other ways that did work, 2 involved computer vision. So we look at the pixels. You see that white rectangle. That's going to be critical. And another was dynamic client hooks. But in any case, we extract this information. But getting the XY location is wonderful. It's great. So it's the creme de la creme, but it's not everything. We need more. Because even if you have the XY location, look at this team fight. You see there's, even around here, so there's 4 red guys, 4 blue guys. Blue team starts in the bottom left, red team starts in the bottom right. The point of League of Legends is you want to get to take over your enemy team's nexus before they take over yours. This seems like it's a 4-on-4 team fight because you have the XY location data. They're all next to each other. But look at the positioning. Wukong, the Monkey King, just flashing into the middle. He's trying to kill people. He's going to blame the team. The team's going to blame him because the positioning is off. So you need an extra layer of analytics over and above the data to figure out what kind of team fight was it? What kind of engagement was it? Did it change over time? Were people positioned correctly? What else can we see? We see the fog of war. Now, I'm not a great League of Legends player. I'm pretty low in the ranking. As people climb higher in the ranking, then they get to pros, League of Legends becomes not a game about kills and deaths, but about vision. And the fog of war is where you don't see. You reduce the fog of war by placing wards, and you reduce the enemy team's vision by deleting their wards, by killing their wards. We can get that information as well. We can see the turret health, not just whether it was dead or alive, but actually how much health is remaining. That's me in the top. You can see Teemo at the top. I play Teemo. I like Teemo because he's a very annoying little champ. Nobody likes him. People don't like him as an enemy. They don't like him on your team. Everyone hates Teemo. There's a stream of just Teemo dying over and over. People love it. Why I like playing him, he has one feature that a few other champions have too, which is stealth mode. So XY location is not enough. You also have to know if he in stealth or not. All right, so we have all this information. The basic process is we're going to spectate the game. We're going to extract the information. That information is the official Riot API information, kill, death, assist, items, gold. Very boring, but that's the basic stuff. Here's what we extract, much more stuff. All of the stats that we mentioned, damage, how much damage you're doing to a particular champion, not overall over the whole game, but for each specific person. Was it physical? Was it magic? How much did you take from each particular person? And finally, of course, the excellent location, Y location, wonderful stuff, stealth, velocity, acceleration. Once we have these raw stats, we need to create new metrics. So we generate brand new metrics that have never been tested before, never been seen before in League of Legends, but are the most important ones. If you start looking at your own replays to try to improve, the number one thing you need to look at beyond the minimap, that's what you do in the game, you want to look at your deaths. How did you die? Why did you die? Was it, so that's at the bottom. Did you die because there's a numbers difference? You went into a 2v4 team fight. Bad idea. Were you lacking vision? Did you not have a ward? Were you ganked? Was there a big health difference or an item advantage? Even raw ability counts are useful. How many times did you just use Q, W, E, R? Combos, if you did a Q auto attack, E auto attack, was that better than an E auto attack WQ, right? And for a particular champion in a particular matchup, each one might be different, so we had that information. What percentage of the time were you doing useful activities as opposed to just kind of wasting your time? Were you laning, were you fighting, were you roaming, were you participating in an objective like a Baron or a Dragon? And finally, team fights. So remember, team fights is a complicated thing. We built a system to figure it out. But just knowing that you're in favorable team fights helps you a lot. What percentage of the team fights that you were in your advantage, at least in numbers? Okay. So once you generate data, we need to have good visualizations. That's the first thing you do. What's the first thing you do when you get XY location data? You make a heat map. Heat maps sometimes help, sometimes don't. In this case, they tell a wonderful story. This is clearly a mid laner, right? This is a guy who focused on mid. He started at the bottom left. He worked his way up. You can see he focused. He got the first tower pretty early. He spent a lot of the game pressuring the second tower. He helped take Baron. He ganked bot. And eventually pushed in and won. Nice. Ward maps, these are useful. These visualizations we created in order to perform an automated player analysis and improvement system for people who didn't have access to this good data before. All you have access to the base raw scores, the raw box scores. So if you can see yourself improve in all of these metrics, you can get better. So a ward map is similar to a heat map, but it just shows where you placed your ward, how they died, why they died, were they deleted, did they expire. And you can see in this particular case, there's not much vision in the bottom left, in the bottom right, because the team is very aggressive. They pushed up. There's no need to ward behind you. Does that make sense? Vision analysis, this one's my favorite graph because it shows, as I was mentioning before, in higher ELOs, it becomes a game of vision. The blue chart is your team's vision. Green is your contribution to the team's vision. Red is the enemy team's vision. And the yellow is the net vision. So what happened in this game? You started off flat vision, got an advantage, lost it, got an advantage, lost it, got an advantage, kept it, won. Time management tells you how are you spending your time, and if it was wasted, the big brown thing you can't even see, it's the wasted portion. You want to reduce that as much as possible. Otherwise, if you're laning, that's good. If you're fighting, that's good. If you're dead, obviously, that's bad. Tilt is a concept borrowed from poker. It's a little different in League. Tilt in League means you're gone crazy, right? You're just loco. You died a few times, and now you're just trying to get back into it because you're so frustrated. So we have this metric for measuring your tilt. It's basically the percentage of overall time your team has spent dead over the past 5 minutes, of which you were the major contributor. If that's around 20%, then that's fine. But as you get higher in 50, 60%, then you're probably tilted. Another thing you can measure as you're watching that graph is what kind of team fights were you in? This guy started off 4v2. Good team fight, but he died. Too bad. 3v3. That's okay, but he died again. And then what happens? He's probably starting to get a little tilted. He's fighting in a 4v5 and losing, 3v4 and losing, 2v4 and losing, right? Yeah, this is my graph. I tilt a lot. All right, so we need to do a win probability model to figure out more advanced stats. We've tried lots of different approaches to the win probability model. This basic one seems to work very well. Just you have the minutes elapsed, the blue and red kills, the blue and red towers, blue and red monsters, and the output variable is whether the team eventually won or lost. We just use a basic machine learning logistic regression with stochastic greedy descent log probability. We create this app. In game, you can put in how you're doing, how many kills you have, how many kills the other team have, how many towers you took, how many barons, and so on. And it'll immediately tell you your win probability. So at 20 minutes is the first time you can forfeit without it being unanimous. And if you see that you have a win probability of like 3 or 4%, then yeah, might as well forfeit. So that's a useful calculator. Given that, we can create an additional visualization, which is an automatically annotated win probability graph. You've seen win probability graphs, but how do you annotate them automatically? We find the lows, the highs, and we specify what was the important context of the game at that time. So you started off at the 11-minute mark, you had a 70% win probability. Why? Because you had 2 net kills over the enemy. But around the 18-minute mark, you're now down to 35% probability. Oh no, why? Because the enemy now has 5 net kills and they took a Drake or a Dragon. All right, all that in mind. The statistical question we want to answer, which is probably the most important question, or one of the most important questions in all of sports analytics for all sports, not just esports, is how much did an individual contribute to a team's performance? It's almost a cliche when you have players scoring lots of points and their team ends up not winning, right? That's a cliche. The individual blames the team blames the individual. Same thing happens in League. Here, for example, if you just look at standard kills. If you're out there getting a lot of kills, it's kind of like getting a lot of points. You're doing pretty well, right? You think you're a carry. You just start feeling good. Your testosterone's going. You have all the juices flowing. But it doesn't necessarily guarantee a win. Even if you're one of the best players across all of our sample, if you had the most kills, you still only have like something like a 70% chance of winning a game. Whereas if you had very poor kills, if you had a very low number of kills, you're not guaranteed to lose. You're still at about a 20% chance, right? This is good. It's good that it goes up. That's just the right slope. Good job, Brian. And it's the same thing you'd probably see with things like points or anything else you might look at sports, right? Something you're doing good, but you're not necessarily winning. But the key, the magic, the holy grail is that gray line. the y equals x gray line. If it could only be closer to that, even a little bit closer, that would be very helpful, right? Because that means it's a real metric that's measuring your real contribution to the team. Well, voila, smart kills. What's a smart kill? How is a smart kill different from a standard kill? A smart kill is a kill that locally improves your probability of your team's winning. So if you kill a guy and then you guys take an objective, that's great. But if you're just chasing around like Singed or something, one of these champions that you just have to chase and you eventually kill him and it takes you 90 seconds, that was a waste of a minute and a half. That was not a smart kill. Smart kills, if you're in the 80th percentile, you have an 80% chance of winning. If you're in the 30th percentile, you have a 30% chance of winning. This is a beautiful stat. I've never seen anything like this before. Similar thing with standard deaths. Standard deaths also, it increases, that's good, but it's not the holy grail. Worthless deaths, that's the holy grail. What's a worthless death? A death could be worth, if you kill 2 of them and you die, worth. If you take out an inhibitor and you die, worth. If someone just kills you for no reason, worthless death, right? So if you have a higher percentile relative to other people of worthless deaths, you're again doing fantastic. Okay. Let's put it all together. If you remember nothing else, just for everybody else in the audience, one useful tool that many people don't know about is called fast and frugal trees. It's a wonderful way of combining lots of information into a unique and simple and effective decision-making tool that has only like 2 or 3 questions, as opposed to a complicated logistic regression that, say, a doctor or a general manager or coach is probably not going to use. But these work well. So we feed it everything, and it spits out what are the key factors and the key decisions that will predict the win probability. And it says 3 things. It finds these 3 stats out of all of the standard and all of the advanced stats that we've introduced. The bottom line is this: don't die for no reason. It's okay to die. Just get something for it. Don't die for no reason. Number 2, get some smart kills, right? If you can get some smart kills. But if you can't do that, at least roam for good map coverage. So help out your team when we can measure what percentage of the map you actually touched. That's a simple rule of thumb. It'll correctly predict your team's outcome 80% of the time. Oh, that's Timo, by the way, so you can see what a cute little guy he is. Bottom line, get good. How do you get good? You use all of our stats, you use our visualizations, and it'll help you get good. So what have we done? We're using a combination of computer vision, dynamic client hooks, machine learning, visualization, logistic regression, large-scale cloud computing, and fast and frugal trees. We analyzed and generated unique data on millions of League of Legends games, calibrated a win probability model, developed enhanced definitions for standard metrics, presented automated improvement analysis, provided a framework for determining an individual contribution to a team's victory, and applied that framework to show that advanced stats both better correlate with and explain team outcomes. All of our code is open sourced as of yesterday morning, and it's under the, of course, MIT license, very permissive. It's available here, github.com/philipmyman/FantasySportsLOL. There's one master branch in 9 different repos, about 4,000 files and about 1 million lines of code, primarily in Go, but also with some JavaScript, R, Python, and Mathematica. Thank you very much.
That was a lot of information. And I just turned 40 this year, so I can now play like the old dude card and be like, I don't understand these newfangled sports. But it looks like very creative work. The question I have is, okay, I'm trying to contextualize it in like a sport I would know, like the NBA or something. If you came to me and you said, we figured out that the key to winning in basketball is to take smart shots and avoid doing stupid stuff, like what mistakes do good players make that your data would correct? Say something you assume is by the community to be a smart strategy is actually an error.
In league or in NBA?
In league.
Ganking is one. So we found that positioning in ganking and in team fights is not necessarily what people would consider optimal. Typically you want tanks in the front, one would say, right? But we found sometimes it might be better to have someone who can flash to the back line, kill somebody and get out, right? Take out their damage dealers. You want to focus your damage. Everybody kind of knows you want to focus on who's the most important target, but they may not have the right target. So we, for example, track who on the enemy team has recently been doing the most damage to your team. That's not necessarily always, in League of Legends, you have 5, not always the AD carry, the bottom line, who's usually the most. It might be a mid lane mage, it might be a jungler who's been fed. So we track that, and then we see how much damage in team fights are you doing to that guy, as opposed to who you think should be the damage dealer, but might not be in this game.
Thank you. I also turned 40 this year, Nate. So I have many questions, but I will limit myself to one. And I'll also draw from the game of basketball. I also want to congratulate you on just sort of being a pioneer in this space. I think this is the first of many such talks.
Thank you.
That we'll see along these lines that Nate and I will struggle to understand. But congratulations on that, seriously. It's a great area. So here's my question. In our sport of basketball, in a room like this, a number of years ago, Dean Oliver came out with a couple, he was one of the first people to sort of do what you're doing for League of Legends. And as he wrote his book, Basketball on Paper, which is a masterpiece, he identified 4 factors that live on today as among the most fundamental indicators or markers of performance in basketball. It was a huge contribution. So here's my question. What is the equivalent of offensive rating or defensive rating? What are the 2 or 3 most explanatory stats in this League of Legends?
Well, 2 answers to that. One is we've been focusing on the individual, and he's focusing on the team, right? He's trying to predict team outcomes based on the variables.
To be fair, he focuses on both. But I
understand, but the ones you're bringing up, those 4 factors.
That's fair. Yeah,
right.
Correct.
So for teams, we've partnered with many of the NALCS teams, and their interests are a little different than individual interests who are trying to climb. There's some overlap in terms of scouting, but much of their interest is in drafting. So we've created separate tools for them, like if their enemy is drafting a top laner, who are they likely to draft? And are they likely to draft top before they draft jungle or whatever? So that's a different win probability model that we would create to fit their needs. Overall in the game, the probability of winning, it's similar to what I've presented here, and from previous research that's not shown here, I can tell you that it seems to be the same top 3 factors. The overall smart kills, the worthless deaths, and the roam, the map coverage. We've certainly found, you would think, similar in basketball, you'd think like scoring or whatever, even ignoring efficiency, the gold differential, which is very available and visible, would seem to be a good predictor, but it's not. Especially in a game like League, you can have a huge gold lead, but if suddenly you're aced late in the game and they can push through and take your nexus, you lose. Right? So gold is okay, but it's not very good for long term. We found that these other stats do a much better job. Does that answer your question?
Yeah.
Thank you.
Wow. So thank you. As someone who's a neophyte in this world, it was amazing to start what you think is going to be an esports conversation, and then weigh the merits of the philosophical idea of a worthless death. So that was a turn I wasn't expecting. My question is kind of a combination of Kirk and Nate's. It's that I'm familiar with League of Legends as a team sport primarily, not necessarily an individual sport. I'm wondering if in your application of this research you found that varying strategies among the team were more successful than every individual pursuing the same strategy.
That a strategy as a team would be more successful than?
A group of individuals trying to optimize to the same performance as opposed to the team optimizing to overall performance.
Yes, that's an important thing. We have a separate area where we created like an esports amateur league where people play together. So typically the way League works, you queue up, you can queue up with maybe a buddy, but you're basically playing by yourself with 4 random strangers against 5 random strangers. But in LCS, the pro leagues, it's like an NBA team. You have 5, they have 5, you know who they are. If you're a regular guy, then you're kind of banning who you think are strong champions, right? Regardless of who you're playing against. But if you're playing against people you know, you want to ban out who their strong players are, right? So we have this league, and we found that coordinated team involvement, including chat, including practicing together, makes an enormous difference. The teams that play together in our league that are similar to like the LCS, one rudimentary little metric, they end up winning something like 70% going forward when they go back to regular stuff, regular team games in League. In terms of specific strategies, it's primarily moving towards where a team fight is or will be seems to be the biggest difference, that kind of coordination. Great players can look at the minimap and they can know where they're supposed to go. People in low elo who are not professionals, they need some somebody to help. They need a shot caller. One thing that we found is that linear shot calling doesn't necessarily work the best. Linear shot calling means you just choose one of the 5 guys and you tell us where to go. Because it's very important to just do whatever the guy says, even if it's the wrong decision. It's better that you all commit than like 3 commit and 2 do something else. We found that that's not necessarily the best. In fact, it's slightly better to have a shot caller for different roles do different things. So warding shot calling should be done by the support. Ganking should primarily be done by the jungler. The top everybody should ping when a guy is missing. But there's very nuanced ways of shot calling. Does that answer your question?
Yes, thank you.
Thank you. Thank you very much.
Our next presenter is Javier Fernandez, who will be presenting Wide Open Spaces, a statistical technique for measuring space creation in professional soccer.
Hello. Well, guys, today we would like to present a project we have been working on since last year, where the main focus has been to try to quantify this concept of space creation in soccer. So when we think about the type of questions soccer coaches ask today, we can see that there's a strong focus on off-ball actions. So if we borrow these words from Johan Cruyff, which is one of the masterminds of modern soccer, he once said that it is proven that players have the ball 3 minutes on average. So the main question is, or the important question is, what do you do during those remaining 87 minutes when you don't have the ball? So he has a strong focus on what are you doing regarding off-ball movements or off-ball actions. So based on this, we just wanted to try to quantify these 2 concepts that are very recurrent and very interesting for coaches. The first one is that of space occupation gain as idea of position itself into areas of greater spatial value. We also wanted to quantify this other similar concept, that is that of space generation. And the idea here is being able to attract opponents to one side and then have a gain of space for teammates. So you generate space for teammates there where the opponent was. So let's see a couple of examples of how this looks. First, of space gain. You can see this player, Paulinho, the one with the red circle. You're going to see that first he just finds himself out of space, and then he just moves away and tries to attack this space right here and be able to control this space and have a greater area to be able to get the ball there. So he's trying to move to help the team playing better. So the next concept is that of space generation. We're going to focus on Andres Iniesta here, the one with the red circle. And several things happen here. First, Iniesta moves backward to try to gain some space, but he's not able to get the ball there. Right now, he's not able to get the ball there. Then he runs into the box to attack this space, and in that moment, he's attracting players, creating a great space for Messi that then is able to receive the ball there. So let's watch this clip again. First, Iniesta moves backward to gain some space, right there, and then he runs into the box. And just when he does it, in that moment, he's attracting these players and generating this great part of space for Messi. So now he's able to pass the ball to Messi, and Messi has a great space to do whatever he wants now. He chooses to do a love pass, which is a good one for Suarez, and creating a very important chance of goal. So when we think about spaces, there's an underlying concept, and it's that of the quality of space. So we believe we can express the quality of space as a function of 2 main factors. The first one is the pitch control, or the level or degree of control you have on a given location on the field. And the second one is the relative field value. How valuable is actually that space you're controlling in that moment? So let's see how we can quantify these 2 concepts and then get back again to space creation and space generation. So regarding pitch control, what we have done is first modeling the player influence area. How much is a player influencing the pitch in a given moment? So if you take a look there to Andres Iniesta, you will see several things. We are placing a bivariate normal distribution on the player's position and then modifying that distribution to account for player's velocity and the relative position of the ball. So also, you're going to see right now that when the ball gets closer to him, he has a smaller spread, and then when he's moving, there's a modification of the distribution to account for its velocity. So once we apply this level of influence each player has on the field to all the players, we have this a surface of control of a given team in a given time that is providing you an idea of what spaces are being controlled by that team. So that's the first part of expression. We have a second part that is the relative field value. And this is an interesting one. We can find that it's very typical in soccer that coaches have this following belief, and also soccer experts, that a given field location has different value depending on context. So context can be many things, but most probably the more granular idea of context here is the position of the ball. This meaning that depending on the position of the ball, there's a different value, or you can value that same location on the field differently. So in order to quantify this, we're just following this hypothesis. That is that most of the time, the opponent is positioned into places of greater spatial value. So what we're saying here is that if we take that level, that overall level of influence that a given team has, actually the defending team has, with different positions of the ball, that team is placing to cover spaces of greater value. So we just took 20 matches and trained a neural network to learn the relationship between the position of the ball and that value, or the value of that, or even of every given location on the field. So this looks the following way. You will be able to see here that when the ball moves right to left, there's a shift also from right to left of the value of the field. And also, when the ball gets closer to the opponent's box, there's an increased level of value surrounding the ball. So what this means is that if you're able to generate space in those places in which you have more reddish zone, so you're going to generate space of higher value than if you do it in the green areas. So having this, we have a way of quantifying the quality of space in a given moment. So now we can get back to the two main concepts of this study. The first one is that of space gain, and we say that there's a space gain if in a given time window, the difference of quality of space, that is the gain in space, is above a given threshold. So I believe it's very important to remark here that there's no kind of ground truth or label data in soccer for spatial movement or for quantifying spaces. So we have gathered with several coaches of FC Barcelona, first team, second team, and youth team for several weeks and watched hundreds of videos to decide that threshold above which we're actually getting to quantify that concept of space gain. So following a similar idea, we have that of space generation gain. And here we first quantify when you're actually attracting a player towards your position. And if there's a gain there where the opponent was, then we just say there's a space generation gain. That means you are generating space for your teammate in that area. So this is how this looks. You can see players with the green circles are players that are in that moment gaining space through movements, right? So now we can also see the pitch control of the whole team. And for example, in this case, Messi is able to recognize Jordi Alba there is having a space of value. He's able to put the ball there, and we have one that was a very, very, very critical goal this season. So definitely, we will be able to generate some season-wide stats with this concept of space generation and space creation, but we believe now that soccer coaches are very focused on being able to analyze single matches, right? So what we have here is in the first row, you have a heat map when players were gaining space, and in the second row, a heat map of where players were generating space. So very quickly, we have in the first column, Sergi Busquets, that is probably the best player in the world, or one of the top 3 players in the world doing this. And you can see how he's able to control and to gain space in the whole mid lane of the field. But more importantly, he's able to generate space almost all around the field. He's able to do, or to enhance this very well known from him pivoting skills and be able to contribute with the team creation and the team open play all around the field. So a second very different case is that of Gerard Piqué, who is a central defender. So he's able to gain space in a small zone within the field, but he's not able to generate space almost nowhere, right? But there's a common case of Busquets and Piqué that they're both able to generate space within the box. And it's interesting when you get back and look and watch the videos, they are doing this in corner kicks and in free kicks. And they actually have this role of dragging opponents when you have a free kick or a corner kick to free up space so the other players can head there, right? So some of the things we can see with this matrix is who is generating space for whom, right? So we have in the y-axis players that are the space generators, and in the x-axis players that are the space receivers. So several things to observe here. This is for one match of last season. You can see that Sergio Busquets is able to generate space almost for every other player on the team, and to also receive space from almost every other player. It's a similar thing that we were seeing on the heat map, but it's very remarkable for him and given his position to be able to actually do this. Another interesting thing is in this match we have Suarez, Neymar, and Messi. And it's interesting to see that it's not just about putting 3 skillful players on top. They're also able to collaborate with movements and be able to generate space for each other. So all the things you can see here, we have here Sergio Roberto, who is a right back, and Lucas Digne is a left back. So it was Lucas Digne's first season, and you can see here that he was not able to generate space for no one. So this might be due to several reasons. Maybe it's an order from the coach. Maybe he's in the same lane as Neymar, and Neymar is dragging too many people with him, but definitely you can be able to recognize here there's something happening. Then we just get back with coaches and watch videos and analyze if the player is actually moving in the right ways and compare with the right back to see how he's performing in that role. So if we rank these players according to the gain of space, we have that the top 3 players are Iniesta, Busquets, and Messi. And probably any ranking is flawed, but it's probably a good thing for the model that's seeing that 3 of the top 5 players of doing this in the world, this is world renowned, happen to be in the top in this list. But a more interesting thing is that we have structured this concept of a space gain into 2 other concepts that are active and passive space gain. So we say that a player is gaining space actively if he's above jogging speed, and passively if he's jogging, walking, or standing. So if you see most players, we have a relationship of 6-4, 7-3, where space is commonly gained actively. But Messi shows an inverse one. He's gaining more space passively than actively. So when we took a look back to the last match against Real Madrid in December, the Spanish press was saying things like this. Messi's playing 83% of El Clásico walking, his teammates are running for him, or Messi played El Clásico walking, or how to win El Clásico walking, and so on. So we get back to a very old discussion in soccer, in which we still believe, and many people still believe, that when the player runs more, he's going to perform better. And it's typically being said that when they do not run, they're not actually performing, right? So let's see how Messi able to gain space of value just by walking or jogging. So in this match, you can see here that he first jogs a little bit away from the defenders, and he's able to walk into a position of value. Suarez is able to recognize this. He passes to Messi. He's able to shot with a little bit of the help of the goalkeeper. We have a very nice goal, right? So just wrapping this up a little bit, it's very important in soccer, which is a a sport in which you have great dimensions of fields and 22 players and probably some unknown dynamics there to try to quantify off-ball movements. This is a thing that coaches talk about during trainings and during matches and during any moment. So in order to grasp a more clear idea of how coaches think about this thing of spaces and off-ball actions, we can borrow these words from Pep Guardiola. So he once said, "We have to pass the ball, yes, but with clear intention. So we pass it to drag players to one side, then creating space in the opposite side. And when we have done that, we move the ball there, and that's our game." Thank you very much.
Good work. So you infer which space is most valuable based on where defense is empirically, right? That wherever the defense is, you assume that's the most valuable territory?
Yeah, I mean, the main idea there was how can we create a generalized model of what spaces are more valuable depending on the position of the ball. So definitely, given a successful attack, you will be able to break that. And in several very particular moments, defense is not going to be placed in the best position possible. But in general terms, and in particular in soccer, where you have probably 15 to 20 chances in one match, you can definitely see how they place in places where it's more valuable to be. So they're trying to avoid that you get the ball there. So what we're just trying to say is, how do we account for that thing that in soccer we have such a wide field that is you're not able to know if in a given moment creating space close to your box has value or has more value to create it in a different place.
But if teams are using the wrong defensive strategy, then your metric in some sense would coach or coax teams toward that incorrect strategy, right? Or I don't know. I'm just saying, like, because it's cool and it seems good that like you're getting kind of quantified estimates of this quote unquote intangible value that good midfielders have, for example, or space creators. But it also seems like, you know, what if teams are defending poorly? Then I don't know. Is that a valid critique or?
Yeah, it's a great point. Nice thing we just try to apply here this model presented in slow, I think 2 or 3 years ago, that of NBA court reality that was valuing where you place and you pass. So when we just saw that on soccer, it was interesting that the valuable places were near the left and right lane, and there was no value near the box. So we asked coaches and said, if I will ask you what are the valuable spaces in soccer, what would you say? Inside the box, just outside from the box, and so on. So we just realized that this model was saying that in soccer it's so hard to get the ball where the valuable space is that we just couldn't find that. But analyzing the attacking movements or the attacking actions of players, but we just tried to get that all around and say, okay, what if the opponent team is actually placing themselves in the spaces of value. So we're just trying to generalize from that, and definitely it's going to be cases in which they're going to be broken out and not well placed. But we definitely believe that in general terms, with a sufficient amount of data, you will be able to capture that. And we also validate these videos with coaches, and they were, at that moment, happy with the results of the idea of where were those valuable spaces.
Thank you. Good work. I think my question's coming again from the sport of basketball, which is tackling similar stuff. Space has entered our discourse a lot in the last decade, and understanding that is key to understanding our game right now. I want to challenge you a little bit on the concept of, do individual players create space? Number one. Do pairs of players create space? Does the ball create space? Or does opportunity create space? Does threat create space? At this conference, we always want to ascribe things to individual players because it's convenient and it's attractive. Is this an instance, again, where perhaps this is more ecological and inconvenient and again, our sport is trying to reconcile the value of space right now. Is this something that we can put on one player? Or is this more aptly looked at with 3 players or 7 players?
Great. So if you take a look to basketball and baseball, you're definitely able to value players, and if you have rankings for several stats for players, that's able to say something about the performance of players and the contribution of players to the team, right? So in soccer, up to this day, we haven't been able to do that. Probably it's about different kind of things, and definitely the concept of space or moving in space sounds a little bit vague, right? So when you ask coaches, actually the whole terminology on soccer is being vague. It's not as direct and discrete and as objective as you will probably find it in basketball and baseball. So we don't believe that for this moment there's an ongoing issue here, that is, how do you attribute, for example, space gain or space generation, right? Because probably Iniesta was moving there and dragging players, but probably Messi was also doing things. So how can you attribute who is creating space and how many players are those? So we don't want to ask that question yet, although it's interesting for some other reasons. But we do believe that the interesting thing here is to be able to recognize when these things happen and saying, okay, in this moment we are generating space as a team. We attribute that to players so we can also do some other kind of comparisons. But we just want to be able to say now, and what we think is more valuable now, okay, coach, you have these clips. In this moment, these players were generating space. Please evaluate this visually. That is what we're doing in soccer now. We're always trying to match any kind of stats and visuals with video, and trying to understand what do they see in video, right? So an interesting case in an individual way is Paulinho. Is a new player we have this year, and it's well known that for Barcelona new players, it takes some time to adapt to that style of playing. So when we see these stats season-wide this season, it's interesting to just see that regarding on-ball actions, he's okay, but regarding off-ball actions, he's a great player. And we also saw the evolution of him from the first match to the last match. But at the end, I think the most interesting thing is being able to get clips from that and provide that to soccer analysts and to coaches and say, okay, this is happening. What can we say here? And since it changes so much from match to match, we're also doing that per match, right?
That was great. Thank you. I had one question that this was very FC Barca focused. And my question is, how much do the coach tactics and formations lead into this? For example, have you tried to test this approach against teams that play primarily on the counterattack or any other offensive strategies?
Yeah, it's a great question. So we have something, I don't know if I'm even able to say it, but we have some issues in Spain for getting data. It's not that easy as in Premier League and Bundesliga. We have to buy data right now. So it's not easy to have tracking data of all the opponents and the different teams, right? So that's why we're now trying to focus a lot on our youth teams, on our first team, and trying to see how our game develops from that. And probably that's also why we're looking a lot at single matches and say, okay, how are we performing against these different types of teams, right? But anyway, as a next step, definitely is what we believe is in general terms is that we have to start in soccer to segment the match in more constrained, in smaller time windows regarding two contexts. There's people doing probably nice things, but taking into account a whole match. And soccer is so dynamical that when you ask coaches, they're typically seeing 3, 5, 6, 10 seconds clips or per attack, right? So it will be definitely interesting to analyze these stats in different types of attack. Definitely, you will be able to generate and create more space when you have what we call a positional attack, in which you're actually building up and have some control. Some other things happens in counterattack when there's a more intense gain of space because you're breaking the whole defense, and that's probably a different way of generating that. Definitely, you can also split and have a different vision for corner kicks and free kicks, right? So yeah, it's a great point. That's why we haven't done it yet, but definitely it's a next step for these things. Okay, thank you. Bye.
Next up, we have Michael Alcorn, who will be presenting Batter Pitcher 2VEC, statistic-free talent models with neural player networks.
Hey everyone, thanks for being here. Today I'm going to be talking about a project I worked on called Batter Pitcher 2VEC. Before I get started, I want to mention that I have a Jupyter notebook up on GitHub that will allow you to reproduce all of the results I'm going to be showing you here. So the idea of quantifying player talent or style is not a new one, and it's been explored in several different sports and been presented at Sloan, as all these papers were. And I have these papers split into two columns that I think reflects two overarching themes I've noticed. On the left-hand side, we have strategies that are what I call, or what I'm referred to as aggregate and extract, where they basically aggregated a bunch of data from their sport for their athletes, and then use some typically unsupervised learning algorithm to try to extract features that quantify player style. The problem with that approach is that aggregating removes any sort of context. And as we all know as sports fans, context is really important when trying to understand an athlete's talent. On the right-hand side, we have models that do incorporate more contextual information by modeling the events of a basketball game by considering the different players that are on the court at the same time. But these models are strictly linear, and so they're not incorporating any latent feature components. And I think we can all agree that there are probably hidden talent variables that explain a lot of what we see in sports. And so what I'm going to be trying to argue today is that this neural embedding framework allows you to marry the best of both worlds, taking the power of these latent feature models and incorporating both the predictive and the contextual aspects of these linear models here on the right. So why are neural networks particularly appropriate for this task? It's because they're good at what is known as, what's referred to as representation learning. Another way of saying that is automatic feature extraction. And so one particular example of this idea is the algorithm known as word2vec. And so when you have categorical data in machine learning, the typical way you represent that is as what's known as one-hot encodings. And so we can imagine that we have a set a vocabulary of 3 words, dog, cat, and constitutional. The way we would convert those into one-hot encodings is by, for each word, assign it an index and give it a vector that's all zeros except for a 1 that's in the index associated with that particular word. The problem with one-hot encodings is that they're implicitly saying everything in the set is equally similar or dissimilar. And so what the word2vec algorithm tries to do is learn a distributed representation of words such that the geometric properties of these vectors reflect some semantic similarity. So words that are close in this space are similar semantically. And the way it does that is by, in this case, I'm talking about the continuous bag of words model on the left here, that particular architecture. It sweeps a window of size 3 over a big text data set. And for each window, it takes the words that are on the left and on the right, it embeds them into a dense vector, adds those vectors together, and then tries to predict the word that is in the middle. And these word vectors end up actually doing what I described earlier, where vectors that are similar in meaning are close to each other in the space, but they're also capable of analogies. So for example, if you take the word vector for Firefox, subtract the word vector for Linux, and add the word vector for Windows, you get a word vector that's very close to the word vector for Internet Explorer. And so this embedding framework is a really powerful way to model discrete data. And so what I was wondering is, can I apply these representation learning concepts to baseball players? And so what I did is I acquired a bunch of at-bat data, where each data point is a batter, a pitcher, and the at-bat outcome. And these are the different outcomes that were possible. So it's basically whether or not it was a hit, who first fielded the ball, whether it's a strikeout, a walk, etc. And so the batter-pitcher-2vec model architecture, which you can see here and should hopefully remind you of the word2vec model architecture, what it consists of is it takes your batter one-hot encoding, your pitcher one-hot encoding, embeds them into a dense representation, concatenates those vectors together, and then tries to predict the outcome of the at-bat. And then the model is just trained, trying to minimize the average cross entropy, which is equivalent to trying to maximize the likelihood of the model. So one interesting thing to note is that people hear neural networks, they think complex or whatever. But if you actually compare the number of parameters in batter-pitcher to vec to a multinomial logistic regression model trying to do the same task, it actually has the fifth of the number of parameters. And so that's just something to keep in mind as we go forward. The first thing we can do after we train the model is try to visualize the embeddings and see if they're doing anything that reflects reality. And so what we see here are the first two principal components of the batter embeddings. And you can see that players with high singles rates are on one end, players with low singles rates on the other end, likewise with home runs. And we can see that batters are clearly being separated on their handedness. And so the model is learning something about the world, but this isn't super interesting because we're already keeping track of these stats, right? But what's a little more interesting is we can take a look at the neighborhoods of these embeddings. And so what we see here are two-dimensional T-SNE maps of the batters on the left and the pitchers on the right. And so we can see, for example, that D. Gordon and Ichiro Suzuki are in a neighborhood together. Mike Trout and Paul Goldschmidt are in a neighborhood together. And what I think is even more interesting is thinking about the pitchers. So we see that Aroldis Chapman and Delvin Betances are in the same neighborhood. And so these are both two relief pitchers who are really, really powerful relief pitchers. And again, the model learned this just by trying to predict the outcome of an at-bat given a batter and pitcher. And so one sort of fun thing you can also do is analogies with these embeddings. And so we can take, for example, the batter embedding for Mike Trout, who's a right-handed batter, subtract the average batter vector for right-handed batters, and then add the average vector for left-handed batters, and you get a vector that's very close to the vector for Bryce Harper, who you might consider Mike Trout's left-handed doppelganger. And so again, this is just another piece of evidence that these embeddings are learning something real about the world. But the real test of whether or not these embeddings are learning meaningful features about these players is whether or not they can predict something about the future. And so what I did is the model was trained on data from 2013 through 2015. I assembled a data set of at-bats that were previously unseen matchups. So these were batter-pitcher pairs that were never seen in the training set. And I compared it to a naive prediction strategy that just basically used a co-occurrence matrix for batters and pitchers. And what you can see is that batter-pitcher to vec was significantly more accurate than the naive approach, and this is at the less than 0.001 level. But perhaps more interesting, or equally interesting, is the fact that multinomial logistic regression, trained and tested on the same data set, was actually slightly worse than the naive approach. And so I think this is a cool proof of concept that these player embeddings can be useful ways of modeling player talent. And in fact, I think they could be applied to other sports in general, including all of these papers I mentioned at the beginning of the talk. But where I think this idea could be really interesting is in modeling spatiotemporal data. And so a lot of sports papers that are trying to model spatiotemporal aspects have this problem of player identity, where they usually have to sacrifice that particular information. And to be specific, there was a paper in 2016 at Sloan that was trying to classify NBA plays using neural networks. And the way they did that is they turned this spatiotemporal data into a sequence of images where they assigned the players to a position using some other task, some other model. And so that's what the colors represent in that image. But when you do that, you're losing all the information about the player identity, right? And so what I want to propose is that you could actually use this image-like data strategy, but use the channels. So usually with images, the red RGB channels are the third dimension of your representation, your data representation. You can use that third channel as your talent embedding. And so what you could theoretically do is acquire NBA spatiotemporal data, for example, and have each sequence, each image, right, have the XY coordinates and in the Z direction embed that player's talent. And then you could try to, for example, build you could use a recurrent convolutional neural network to try to predict whether or not that play resulted in a made basket. And once you do that, you actually have a model that you could use for model-based reinforcement learning. And I think that's really exciting because at that point, you can start having an AI designing plays. And as we've seen with AlphaGo, the AI that beat the best humans in Go, these AIs that learn to play these games at superhuman levels are using these really creative strategies and things that have never been seen by humans before. So I think that the potential of an AI designing plays is a really exciting one. And that's all I got. Happy to take questions.
So when you showed that two-dimensional chart, Mike Trout and Bryce Harper were fairly far apart.
Yes.
But if you account for handedness, they're very similar.
Yes.
Okay. So why is handedness so important? Because to me, I wonder, like, maybe all you're really capturing is the platoon advantage.
The what advantage?
The platoon advantage. So, like, if you predict out of sample well, you're just saying that, okay, well, left-handed hitters do well against right-handed pitchers and vice versa. I'm just wondering why handedness is so important, because it seems like not essential to the way that I would define different classes of baseball players.
It's not important. It's just the dimension of their talent. So, like, the model, the possible outcomes included who first fielded the ball, and so like left-handed and right-handed hitters have like different biases, right? And so like if you just these analogies are essentially like moving players in the space. So you're like changing Mike Trout into a left-handed batter essentially, and who would that look like? So it's not like it's necessarily important. It just defines their talent overall, I guess.
Okay.
Thanks. Great work. My question is pretty simple. It's the classic so what question. So let's say I'm working for a baseball team. You come in, and now what are we doing? What are we doing? What are we doing? What does this model let me do? Am I picking players? Am I organizing? So what? It's the baseball analytics question. How does this impact my team on the ground?
Yes, I mean, I think the idea is that you could use this as part of your models that are trying to, I'm assuming baseball teams are trying to simulate games, and this would be a better way to represent your players rather than just using raw statistics, and so you would get more accurate estimates of at-bat outcomes. Than when you simulate your games, you have a better idea of whether or not you're going to win, and so you can evaluate trades and I mean, I don't know if that's what's actually being done. I'm not in baseball, but that would be something I would think would be useful.
Thank you. And I just want to be on the record that I welcome our robot overlords. So thank you. Yeah, so I wonder if, I do wonder, it's sort of building on Nate's question, I wonder if this really is just better categorized as sort of a player classification tool, as opposed to just identifying, maybe one of the applications would be all-star selection or identifying diamonds in the rough for player evaluation in terms of signing new free agents that better meet the deficiencies in your current lineup, something like that. Can you expand a little bit on other sport applications, though? Maybe it's just because I'm the liberal arts guy in the room, but when we got to the third vector, I kind of glazed over a little bit.
Yes, I mean, like, if your goal in these various sports is to try to model the player's talent or the athlete's talent to try and basically, I'm just like thinking about like forecasting. Like if you're trying to optimize your team and you're trying to, the way you have to, like, I think about it from like a reinforcement learning perspective, right? If you're trying to optimize some outcome like wins or whatever, you have to know how the athletes involved are leading to the different outcomes that eventually lead to a win. So like I'm thinking about it in like a simulation framework. So you like build a good model of the player's talent and how these, like I think the spatiotemporal is actually the most interesting part of my paper. You build this really accurate model of how the players and their talent are interacting in these spatiotemporal contexts. Then you can try different things basically to see how that leads to better outcomes eventually for your team.
Got it. So it's more of an additive to different models that already take into account different areas and roles on the team, as opposed to taking the discrete part of the pitcher-batter matchup and applying that specifically.
Yeah, and so I think like in the context of basketball, it's interesting because like using like a position assignment is like not really capturing the nuance of like a player like LeBron who's like shifting around, right? Like, and so you're just embedding their talent. and allowing the model to just look at the talent and not really consider these like hard classifications that aren't necessarily real. It's convenient for humans, right?
Great. Yeah, got it. Thank you.
Thank you.
Our final presentation today is going to be from Addie and Andrew, who will be presenting Ghostbusters, real-time interactive play sketching with synthesized NBA defenses.
No, we have one up here.
Good afternoon, everyone. I'm Adi, and this is Andrew, and we're here to present our work on real-time interactive play sketching with synthesized NBA defenses. As you're probably guessing, we had a slightly different name in mind, but it was trademarked, so we went ahead with Ghostbusters instead. Over the last 5-6 years, there's been some amazing work done in sports analytics, a lot of which you guys have actually seen at this conference. And more recently, that analytics has become a lot more fine-grained, but it still finds its place either pre-game for planning and scouting purposes or post-game to analyze team and player performance. But what about courtside? Imagine that the Boston Celtics are down by 2 in a clutch playoff game with 5 seconds left in the fourth quarter. Where does all of that analytics go? All a coach has is intuition from pre-game planning and scouting reports. So what we want to do here is, the question is, how can we bring that analytics from the back office, courtside, to help make these in-game decisions? And Ghostbusters is our answer to that. Ghostbusters is an intelligent sketching interface that allows a coach to intuitively sketch out a play just like he would on a traditional clipboard. And now, once we have that sketch, we actually extract the timing information from it, and we can do a few cool things with that now. We can firstly animate that sketch to get a better understanding of what that sketch entails and what players need to be doing. But more importantly, we can then bring back all of that analytics that we have and in real time generate the defensive response of your opponents to see if that play can bust the ghosts.
All right, so Adi introduced our tool Ghostbusters here, which is really built on 2 key elements. And the first of these is sort of improved ghosting models that synthesize very context and team-specific defensive behaviors, okay? And so the origin of this was really a project by the Toronto Raptors back in 2013. They wanted to improve on the defensive side of the ball, so their coaching staff went through game film by game film and labeled where each of their players should have been. They called these things ghosts. And it created a tool that they could show players and coaches about where they were systematically out of position. This is hugely time-intensive and inherently subjective. And so another approach was to do this in an unsupervised, data-driven approach. So there was some work last year presented on data-driven ghosting. This work still had some really important limitations, though, that made it not really an in-game or courtside tool. It lacked the sort of contextual awareness that players and teams perform differently in different game states, and just as a factor of performance degradation throughout the game. Additionally, that was all restricted to past offensive events. We could never ask what-if questions about a new play or a new situation. And finally, they lived in servers and not on the sideline. So our ghosting models are built on contextual imitation learning. And there's kind of 4 key points that I want to just highlight that are essential to making this work in the context of team sports. The first thing is you need enough data. You need these teaching examples for your model to emulate. So everything we're going to show you here is from 30,000 possessions from the 2016-17 NBA season. Having that data is great, but we also have to route it to our 5 individual models in an intelligent way. And we want each of these models to have a coherent defensive identity and begin to learn relationships between each other, which means that we have to route each data point based on the role it's filling in that possession and not necessarily the position on the team sheet. Perhaps the most important thing is how we represent the world. In order for these models to learn how to play basketball, we want to do some of the heavy lifting for them. So we represent each player's position in an over-complete way. That means essentially we're doing all the 10th grade geometry for it.
We not only do its x, y coordinates, but also its distance and angle to relevant features like the basket and the ball. And then we also include contextual features, both on a player-specific level, so things like how many minutes you've played or how many fouls you have, as well as sort of global game state context. And that can be things like shot clock or score differential. Finally, the model itself needs to be both deep in structure, and it needs to be trained in a way that's deep in time. This is where we start to see things like chemistry or the ability to anticipate or recover. So what does this get us? I mean, we'd like to see the behaviors that we associate with NBA defense. So I'm just going to highlight some of the sort of atomic level behaviors we see. So we see people play help defense. We see the sort of blue circle come off his own man to prevent a layup. We see ghosts fight over screens to stay glued to shooters, which is interesting because they don't actually have any physical volume. We see them close out along the three-point line. 2016-17, this is an important defensive thing. And we even see the court awareness that they will selectively apply ball pressure when they have a chance to force a backcourt violation. So all of these atomic behaviors are great, but again, when we're talking about predicting in-game, making real trustworthy forecasts, we need to account for all the different ways that players and teams change, both in their motivation and performance. And so including these contextual features is really important, and I want to kind of highlight this with a couple of visual examples. We have a player driving to the basket, and we can go in and take that on-ball defender and say, you haven't played 4 minutes, you've played 44 minutes. And given the examples that we've seen in the data, that ghost knows that it's not keeping up, right? It starts to lag behind, and teammates try to fill in that gap. Alternatively, we could say, instead of being tired, you actually have 4 fouls. What does that do to your positioning as this player drives into the lane? And you can see that the player takes a much more conservative approach, dropping back rather than being right on his hip. Finally, seasons themselves are a contextual feature. And we can ask, how has NBA defense changed? So the really light gray circles were trained on data from 2013, and the darker gray circles on 2017. And we can see an increased emphasis on guarding the three-point line. Okay, so these ghosts imitate high-level context-dependent behaviors, but I want to make a stronger claim that the trajectories are nearly indistinguishable from real data. But I'll let you guys kind of make your own judgment. So we're going to show you 4 8-second clips, and in each case, the red dots represent real offensive trajectory data. And the dots of the various colors are defenses that you have to determine whether they are real tracking data as well, or synthesized by our ghosting models. So first we have, dots in the Oklahoma City colors. And then in Celtics green. Pistons blue. And finally, Warriors blue. So here they are one final time. Which are real and which are ghosts? It turns out 3 of these are all synthesized by our model, and only the Celtics green was real trajectory data. So it passes the eye test, or at least I think so. But we need to have a discussion about trust. If we want this to be courtside, if we want this to be used by coaches, it's important to remember that not all errors are equivalent, and we need to be very conscious about where our models make mistakes and how they do. One of the first things we did is we took ghost-generated trajectories and real trajectories and fed them through an expected points model. And we see those 2 traces are very close. And that's important to say that the on-ball defense is functionally equivalent. Additionally, we're predicting out into the future 6, 8 seconds, and the absolute errors don't blow up. And in fact, basketball is such a structured game that the error actually collapses at key moments like shots and screens.
What we've seen until now is an in-depth understanding of what these improved ghosting models are capable of, and hopefully we've convinced you that these can actually make realistic context-specific behavior that you can actually trust. But that's only half the battle. What we now need is a way of actually interacting with these ghosting models. And more importantly, we need a way to actually get this courtside. So what gets us courtside? We have 3 constraints that we're working with here. One is constraint from the coach, in a sense that we need 0 barrier to entry. This tool needs to be just as easy to use as sketching on paper or a regular clipboard. We have constraints from our analytics and from these ghosting models in a sense that they require tracking data and not a sketch. So the question is, how do we generate NBA-like trajectory data from a sketch? And thirdly, we have a constraint from the setting. This tool needs to be intuitive. It needs to be something that runs on a laptop. You can't have your analytics staff or coders sitting on the sideline on the bench helping you out during a timeout. So what do we mean when we say 0 barrier to entry? Like I said, it needs to be something that's just as easy to sketch on as it would be on a regular clipboard. And you can't have like a clunky interface that has drop-down menus and mouse drags that make play sketching actually a cumbersome process. And given that Boastcasters is actually a smart tool, it can automatically identify ball movement and infer the state of the ball. Once we infer the state of the ball, we satisfy these causal constraints that allow us to segment our sketch and actually convert it to trajectory data. Now, we're back to that question. You're down by 2 with 5 seconds left in the 4th quarter. In a clutch playoff game, Brad Stevens draws out his end-of-game set winner, where you're trying to create open space for your shooting guard with the help of a couple of screens. This is what it looks like on Boastcasters. And now, let's say you're in a first-round playoff game and you know that you're playing against the Chicago Bulls. What you'd like to see here is how the Chicago Bulls are likely to defend this. And that can give you insight into whether this play is the best for this situation. And with Boastcasters, you can actually import offensive trajectories. And with something as easy as just scribbling out segments, you can now draw out a new sketch and append this and see if you can answer these what-if questions that we could never do before, to see if this new sketch can actually give you something that has higher expected points. With that, I'd like to thank my team of co-authors, and we had a lot of fun doing this. If you guys want to try out Boastcasters, we have a couple of iPads here, and you can have fun. Thank you so much.
Good work. So I have a couple of questions. One is, you're making inferences on defensive positioning based on some entire set of NBA plays throughout the game.
Yes.
I mean, things are a lot different in the half court, in an inbounds play, in a timeout setting.
Yes.
What if you train your model based, I mean, it's a much, much more limited sample size, right? But what if you looked for analogous settings? How different do the ghosting positions look?
So they look different based on settings. Like we focused on looking at half court versus transition opportunities, and you see very different, behavior. But this is something that comes into how you curate your training set, right? If you want this to be accurate in those different circumstances and relate to those different circumstances, those initial ground truth data has to be there. We're not going to be able to tell you something that we've never seen an analogy of before. But if we include transition baskets, we get good transition defense.
Yeah. So you can get something more. So if you want something specific to transition plays, you can, like you said, you can take all of your transition plays that you have from tracking data and possibly train a model just on that. It's going to be a lot better in doing transition defense.
My other question is, what happens if both teams have Boastcasters? If the Bulls know what Brad Stevens is going to run, and they know, I mean, there's some Nash equilibrium here or something, right?
I mean, the NBA would tell you it's a make or miss league, right? It's I'm just joking, but we don't do any sort of optimization on the offensive side yet, right? Like, we're just saying what the defense will do. This isn't a closed game theory loop yet. That'd be fun, but we're not there.
Great stuff, guys. Adi, Andrew, I have a couple questions as well. As somebody who dove into defensive behavior a few years ago. My first question is, what about zone defense? I think one of the common tactics The second coach, right? We talk about Brad Stevens. Let's talk about Fred Hoiberg. What if he decides to put it, there's 5 seconds left, I'm just going to throw a zone out there?
So you do see examples where the defense starts to pick up some zone concepts. I think one of the things that I would think would be really fun to do is train on some college data. Like I would love to train on a bunch of Syracuse data and see what it looks like. But watching through Ghost on trajectories it's never seen before, you will, under certain circumstances for certain teams, start to see very zone kind of handoff behavior.
And I love how you said it, how do you curate your training data set? Are you identifying zone defense and separating it out from man-to-man defense in your training data set at this stage?
Right now, not really. We focus on looking at trajectories just as we get them. We do a few quality checks to make sure that all of the data is actually correct and makes sense, because you don't want to be throwing bad data into your model. But again, to answer that to your first question about what if they play a zone, and if you have, so the thing is, we have to look at the ability of these models here. You can, if you use these along with some scouting reports and pre-game planning, you might have an expectation of whether they're going to run, they might play a zone, they might do this. So this tool can actually give you defenses that are capable of different types, like zone specifically and man. They're capable of doing that. So then you can sketch out plays and see which one works best for which situation.
Okay, one last inconvenient truth.
Yes.
The Golden State Warriors 1 through 5, okay? How are they going to behave? All right, sometimes the 5 is Zaza Pachulia, sometimes the 5 is Draymond Green. Again, how do you curate your training set? Are you accounting for these major tactical differences based on personnel in your training data set?
No. So the answer is that this is a sort of an iterative process where each level we're trying to get to a higher degree of resolution. Currently, team ID encodes a lot. It encodes, a broad, if you have Cavaliers, you have 85% LeBron. He's on the court about that percentage of the time or something. So the next step is to begin to segment players into, I would say, archetypes. And then, hopefully get to the point where you have the resolution of per player and per lineup.
Yeah, because
but we don't have that resolution
again, yet. The last point I'll make along those lines is, if I'm talking about a ghost defender that's named Giannis or a ghost defender that's named Yogi, that dot can be in different places.
Yes.
And should be in different places. But again, don't mistake. This is good work.
Thanks.
Thanks, guys. So you mentioned in your presentation this idea of sort of like a fatigue coefficient. And just given what the answer was to Kirk's questions, could you explain how individual affects larger model drags? Is fatigue actually a factor within your model that you isolate, or how do you?
Not explicitly. So the amount of time that a player's been on the court is in the model, and from there we let the deep neural network begin to associate that with what the ensuing behavior is, right? So we don't say that a tired player should be sluggish, but from the training data, it knows that players that have been on the court for more than 40 minutes don't do these things or do these other things. So this is entirely, we let the model pick up on that. We don't specify any form for that.
So the other thing, that's a great question. I've played 40 minutes.
Right.
Generally, that means there's 2 minutes left and somebody's up by 10.
Right.
I'm not playing hard defense. Again, how are you curating your data set? These guys' behavior in high leverage situations versus low leverage situation is naturally very different. Again, it's just a curation.
Yeah. And so I think to right now, curating that data set is about representing a lot of different teams and a lot of different matchups. But I'm sure if you look through our training data set, we don't have a single situation where a player has 5 fouls in the first quarter. That's part of the state space, but not necessarily a useful part of the state space. 30,000 possessions is the data we had available to us that fit on a GPU. And that's another project, is to curate that data set, grow that data set, and make sure that you are representing all of that, that fine-grained situational stuff in the data, as well as giving the model the capability to pick up on it.
Thank you so much.